Welcome to another edition of Papers We Love, San Francisco. I'm Elaine. I'm the community manager here at Fastly. In case you don't know, Fastly is a really awesome, really fast, and very performant, developer-friendly content delivery network. If you have any questions about the product itself, we have a bunch of developers here in the back. They will also like to tell you that we are hiring most positions, developer and non-developer. So if you're interested in working for us, please let me know. And finally, we are really community-oriented. So if you have your own meetup, open source project, any kind of interesting community thing in the Bay Area or beyond that you'd like to get off the ground, please let us know and let us know how we can help. We're always down to donate our space, give you some free Fastly to speed up your stuff. And any support or manpower that you'd need, we'd be happy to give you. So, yeah, that's about it for me.
All right. So again, administrivia for everybody that returns. We have PWLs in December. I'm just only going to say the next 3 months. So we are covered till September of next year. But if anybody wants to speak, it would be great. And I would be very happy to give you a spot. But in December, we have PWLs on managing update conflicts in Bayou. And in January, we're going to talk about a little bit of data center storages with Alex Rasmussen. And then in February, we have Katie McCaffrey talking about Orleans. So RSVP, if you want to show up, I will probably, if you tell me that you're going to show up and you need a nudge on Twitter, I will be that person for you. And I will call roll today and make sure that I will shame you, very nicely in Twitter if you don't show up. So, so without further ado, we are going to give it to Leif Walsh from our New York City chapter. So he's going to come and tell us about the Level Ancestor Simplified problem. So applause for Leif. Yeah.
Thanks. Hi. Is this good? People can hear me? All right. Great. So I want to talk about the Level Ancestor problem. This is a paper that was written by one of my favorite professors, a founder of our company, and also his friend, who's also a founder. And this is a very similar paper to one that I presented in New York on the least common ancestor problem. So these papers are related in a really nice way that I'm going to talk about at the end. And I encourage you to go at least read that paper, if not, maybe watch that presentation. It's all on the whiteboard, so I don't know, the video might be a little weird, but it was a lot of fun. So, level ancestor problem, what is this? Well, it's a problem of trees, rooted trees. And here, this is not like a balanced tree or a tree with fixed fan out. This is just literally a graph tree. So, nodes, edges, no cycles, a root. That's a tree. And we're going to talk about the depth of nodes in a tree. And so the depth is the number of edges along the shortest path from the root to a given node. So like this node has depth 3, and the root has depth 0. Everyone cool with that? So the level ancestor problem is given a node and a depth, find the ancestor of that node that is at that depth. So if I ask you to find, the level ancestor of this node at depth 3, what I'm asking you for is this one. So we go up the tree until we get to the right depth, and then we say that's the answer to the question. So the paper is basically talking about how do you pre-process a tree quickly so that you can answer queries of this form also quickly. And we're going to talk about these algorithms in terms of their pre-processing time and the query time. And this notation gives basically, this is the pre-processing complexity and this is the query complexity. And everything that we're going to do today, space usage is the same as pre-processing time. So in some cases, those might be different, but here they're all equivalent. So we always like to start out thinking about these problems by coming up with some kind of naive solution. And in this case, it's just don't pre-process it. Just walk up the tree for every query. And if you're asking for nodes at the bottom of the tree, each query could take linear time to answer. Is that clear? Cool. So let's do better than that. And the way that the paper is organized is it goes through a series of progressively more interesting solutions to the problem, and at the end you get a nice result. So first we're going to talk about the table algorithm, which is quadratic time preprocessing, and then queries are constant time. And then there's the jump pointers algorithm, which is n log n to preprocess, and then you can answer queries in log n time. And then we come up with a ladder algorithm, which is a different construction that only happens to take linear time to construct, but then it also lets you answer queries in log n time. And at the end, we're going to combine the jump pointers and the ladder algorithm to get something better, which is going to take just as long to preprocess, but you're now going to get constant time queries, which is kind of cool. So let's go. The table algorithm is easy. You can do this with pretty much any problem as long as you're willing to pay for it. We're just going to pre-compute all possible answers given the tree and store them in a table. And to answer the query, we just look up the answer, right? We've already done all the work. So how long does this take? Well, there's n nodes in the tree. And so that's the first parameter to this. And then the other thing you have to look at is the depth. And the depth of any node could be up to the size of the tree. And so you can ask for any depth lower than that. And so basically what you end up with is you can get up to quadratic space if you have a stick, essentially. Dynamic programming will allow you to compute this actually in n squared time. If you do it naively, it would be n cubed. But the dynamic program is fairly straightforward for this. And then, of course, the query, you're just looking up something in an array. So that's constant time. So at the top, I have the complexity of this, quadratic, preprocessing, and constant time lookup. Now, the jump pointers algorithm is saying, well, you know what? We can probably do better if we don't store every single answer, and we just store some of them. So instead of for each node storing all possible ancestors, we're just going to store a few of them. So we're going to do log n, because it's a tree. You should have some logs somewhere. And we're going to put jump pointers. So basically, at each node, we're going to write down a list of ancestors of this node. The first one's going to be 1 above it. The next one's going to be 2 above it. The next one's going to be 4 above it. The next one's going to be 8 above it. And we're going to process the tree like this. So we're going to have, this is not a very interesting tree, but from this node, you can jump up 1 or 2 or 4. From this node, you can jump up all the way to 8 higher. And you're going to do that at every node. And so this is sort of the things you're going to compute and store. And so the preprocessing is to just create a table where you're doing this for every node, but now instead of storing possibly n different jumps from each node, you're storing these log n jumps. And to answer a query, we're going to basically, from a node, from the query node, we're going to jump up as far as we can without going past the ancestor we want. So we're going to let delta be the depth of the node minus the query depth, this is basically how far we have to travel. And then we're going to take the log of that, take the floor of that, and follow that particular jump pointer up. And so what this is going to look like, and then once you're at that node, now you have less distance to go. In fact, at each point, you travel at least halfway there. And you're going to recursively solve this. And so this is what this looks like. So we start at x. We're looking for the node of depth 2, so we're looking for this one, which means we see, all right, well, we've got like 6 to travel, and 4 is the largest power of 2 less than 6, so we're going to take that pointer. And then we're going to look at its jump pointers, and we're going to use one of them to go farther up. And in this case, we land where we're trying to get. And so now that answers the problem. So preprocessing, how long does this take? Well, there's n nodes, and we're going to have log n pointers per node. And it turns out dynamic programming works here too, because basically you can look at your parent's pointer. You can look at your parent's set of pointers, take all of their jumps, and then from each one of those jumps, go down 1. And so for each of your pointers, you can compute it in constant time, knowing what your parent's pointers were. So that's why dynamic programming works. And so the total preprocessing is n log n. query time, you'll notice if you look at powers of 2 that given whatever your delta is, you're always going to travel by at least half of that distance at every step. So we're going to reach the target in just log n pointer dereferences, essentially. So that gives us n log n preprocessing and log n query. Everyone cool so far? Great. What's next? The ladder algorithm. So consider just a path. So this is that stick we had before. There's no branching, but this is technically a tree. We can preprocess this tree by just storing it in an array, and then no matter what the query is, we just return the element of that array where the depth that we want. And so these sorts of trees are easy to process. So let's try and take a general tree and come up with paths that we can preprocess this way. So we're going to do what's called a long path decomposition, which is where you start out by finding the longest path. That's why it's a long path decomposition. And you identify it, and you remove it from the tree, and you're left with a forest of subtrees. And then we're just going to do this recursively on the remaining trees. So we find the other longest paths of the ones that remain, we remove them, and what we're left with is a forest where each of the trees we've chopped this thing into is a path that we can process with just putting it in an array. So we do this, and we can find any of the ancestors in the component of the node we're queried with in constant time, because you just walk up the ladder, or you jump up the ladder, really. But if we're actually looking for a node higher than that, we have to go to the top of our ladder, or sorry, the top of our component, go up to its parent, and then look in its array, and walk up the tree that way by stepping up these ladders. Which means that the worst case here, it looks like this. And in this case, if your query node is like this one, and these are your path decompositions, however high you're going, you're going to have to jump up. You're going to have to jump up to another ladder for every single level you jump up. And in this case, basically the query is square root of n. And that's not very good, because we had log n before. So we're going to do better. We're going to augment this by basically making all of these paths a little bit longer. And we're going to double some of the nodes so that we can sort of travel farther in all of our ladders. I haven't actually introduced the word ladder yet. I keep saying that. I'm sorry. So for each component, we previously were allocating an array of the component's size and just storing the path in there. What we're actually going to do is we're going to make an array twice as big, and we're going to store the component in the bottom of that. And in the top of it, we're going to store the next parents of the top node. Whatever they were, we're just going to double the size. And so we do a little bit more preprocessing work, but we don't care about constants. And it gives us some nice properties that I'll get into in a minute. So essentially what's going to happen is you've got a tree that looks like this. You are going to do a long path decomposition. And then you're going to take each of those paths and put them into one of these 2h tall ladders. So this longest path, there's nothing above it, so that's just your array. But this one, normally we would have just stored these 3 nodes, but now we're doubling the size of the array, and so we're adding the nodes above it, but then we get to the root and we're done. We do the same thing there. So notice the root is in 3 of these arrays. So we paid some extra storage. For this path, we're doubling it, so these 4 nodes will be in that component's array. And those are the remaining ones. And so we're going to have all of those separate ladders, where a ladder represents a component and then allows nodes of that component to sort of jump up the tree a little bit farther. So what are we going to do? Now we want to talk about the properties of this. So the height of a node, the way we're going to define it for the math, is basically that leaves have height 1, and every node's height is the maximum height of any of its children plus 1. So in this example, this node's height will be 3, because this one has height 1, this one has height 2, this has height 1, but now this one is going to be 3. So that's how we're talking about height here. So what happens? Well, first of all, if we have some node with a certain height, it's going to be in one of these ladders. And because it has some height, h, the top of the ladder is going to be at least that much farther above it. So we can jump. So from any of these nodes, whichever ladder it's in, we can get to nodes of twice its height in constant time. And that's kind of what I just said. You're going to be able to jump up twice as high from any node that you start out in, at least. So the ladder algorithm is to pre-process the tree and construct these ladders, and you can do it with a couple passes of depth first search-ish things. And then you're going to extend each of these components to ladders. And to answer a query, you're going to either jump up to the right depth if the node you're looking for is inside the ladder you have. Otherwise, you go straight to the top of your ladder, go to its parent, and then that parent node is in some other ladder, and you jump up that one too. And you just try again. So it's the same sort of go up as far as you can and keep searching. So pre-processing time turns out to be linear time. The construction of the long path decomposition is fairly straightforward to do with depth first search. And then you might be wondering, well, I'm going to be doubling these nodes that are high up in multiple ladders. Well, whenever you write down a node in a ladder in like the top half, it's basically paid for by the existence of a node below it that sort of is owned by that ladder. So you really only double the work, and we don't care about doubling work. For queries, jumping up to another higher ladder as you're going up the tree searching basically costs order 1 time. So you look at the first element of your ladder, and that is constant. You go to its parent, that's constant. You find the ladder with a pointer, and then you go to the top of it, and you just repeat this. So every time we jump up from one ladder to the next, we're basically getting to another ladder that is at least twice as tall, because of the property earlier where for a given node, the ladder that it's a part of is at least twice as high as the node itself. So when we go to a node that is, I'm going the wrong way. When we go to the next ladder up, it's got to be at least twice as tall. So we sort of go farther and farther each time until we're in a ladder with the ancestor we're looking for. And because we're doubling, essentially you take log n steps no matter where you start. And that gives us the linear time construction and log n time query. Is everyone with me so far? I can go back if we need. OK, cool. So now we're going to attack the problem from both sides. So this happens. And to do that, we're going to think about why jump pointers and ladders work well, or sort of well. They get log n query time, which is OK. Jump pointers allow us to initially go really far up, but then when we get close to the target, we have to start slowing down. So basically, the first jump is going to take us at least halfway there. With ladders, you start out with small movements, but once you get sort of high up in the tree, you can really cover a lot of ground. So once you're in a ladder that is at least halfway to the target from where you started, you're going to get there in one more jump. So let's just do both. We're going to make the jump pointer table and the ladder decomposition. And to query, we notice, well, again, we need to travel up by delta nodes. And so the jump pointer is going to take us basically halfway there. And then we'll take that node's ladder, and it's going to allow us to travel at least that much farther. And we're pretty much done. And so now with one jump pointer and one ladder move, we get there. And so the pre-processing cost is just you add them, so it's n log n. And the query time is actually constant time in this case. So we get this nice result, which is that you can preprocess it in n log n time, and you can query it in constant time. So to recap, we have this data structure, and we get constant time queries for this particular query. And it takes n log n time to preprocess. So we're going to do it faster by using this one weird math trick that is also present in the LCA paper. So how does it work? Suppose you have a problem of size n, and you have an algorithm that you can you have an algorithm you can use on this. What we're going to do is we're going to divide the larger problem into a whole bunch of subproblems of size log n and one sort of super problem of size n over log n. And then we're going to do some math, and some magical things will happen. We're going to use the n log n algorithm, like the one I just described, to solve this super problem, and you plug those numbers in and nice things happen. And then you just have to figure out how to solve problems of size log n, and those are small, so they should be easy to solve, right? So if the size of the super problem is m, we're going to plug some things in. We're going to remember how logs work. We're going to get rid of the minus factor because we're in order notation. Then we're going to cancel the log n's, and we're going to get a linear time algorithm. And this actually works in a lot of crazy cases where you wouldn't expect it. So how are we going to do this? We're going to look through the tree, and we're going to pick jump nodes to be the maximally deep nodes that have at least log n over 4 descendants. And the over 4 is going to matter later. So basically what this picture is showing is these triangles are all subtrees of size less than log over 4, log n over 4. I'll get there. Yes. So each of these triangles is a subproblem of size log n over 4. It's a subtree of size less than log n over 4. And we're going to pick the jump nodes to be the farthest down nodes where all of their children have this property. So in this case, all of these red nodes are such that all of their children have less than log n over 4. So they're the farthest down nodes that still have at least log n over 4 descendants. So this gives us a bunch of small trees, which are of size less than log n. And it gives us one macro tree. Sort of the nodes that are still circles comprise the macro tree. And there are n over log n nodes in that tree. And the leaves of the macro tree are these jump nodes. So what we're going to do is we're only going to compute jump pointers for those red nodes over there. And if you remember when we were doing both the ladder and jump pointers, the ladder algorithm is already linear, so we're trying to improve the jump pointer side of this. So for all the other nodes, we're just going to arbitrarily pick one of those red nodes to be the jump descendant for one of those nodes. And now, when we have a query that happens to be in the top part of the tree, the macro tree, we just pick the jump descendant. We jump down there in constant time. And then we've got the jump pointers. So we use one of the jump pointers to go up, and then we use the ladder to go up the rest of the way. And those are basically 3 constant time operations. So now we've solved the problem for queries in the macro tree in constant time. So now we have to solve the micro trees. Suppose this over here is one of the small trees that we have to deal with. Consider a depth-first search. We're going to go down and visit every edge, essentially, once on the way down and once on the way up. And so we can identify a tree shape with bits in a bit vector, where when we go down, we write down a 0, and we go up, we write down a 1. And we go through this in depth-first order, and we come out with a bit pattern that is as long as twice the number of edges. And this uniquely identifies the shape of the tree. If you have one of these bit vectors, you can just say, all right, I'm doing a depth-first search. I'm going to reconstruct the tree from this. So because every microtree has less than log n over 4 nodes, there are actually not very many possible microtrees that exist. And that's because they're just bits, right? So you do some math and you see, okay, there's actually only square root of n possible different shapes of tree that can be at the bottom of the problem. So we're just going to use the stupid algorithm where we write down every answer, right? And now to answer a query, if we're in the macro tree, we do what we talked about before, and we jump down, and then we jump up, and then we climb the ladder up. If we're in the micro tree, either the answer is somewhere in the micro tree, and so we use the table to solve it, or we just go to the top of it, go to its parent, and then do the macro tree algorithm from there. And then we're done. So, pre-processing. We identify the jump nodes and the macro trees, the jump nodes and their children, the micro trees, with depth first search. We compute jump pointers for the jump nodes in log n time per jump node. So computing all the jump pointers takes that long. And, you use the ladders it's important that you use the ladders when you're constructing these, the jump pointers. Otherwise, you can't actually do it fast enough, but it does work. And then pre-processing one of these microtrees, since the microtree is log n, that is going to cost you log squared of n. And then all microtrees together are this expensive, which is less than linear. The query time, I kind of described it already. We're going to use all of the machinery we've come up with before to solve things in the macro tree. And then in the micro tree, we also do it in constant time. And so we're done. So you pre-process this tree in linear time, which is like, that's how fast it takes you to read the damn thing. And then queries are all constant time. So that's nice. So what have we learned? One nice thing about this paper is it talks about how you can take two different algorithms that sort of support each other's weaknesses, where you have jump pointers that are fast at first and ladders that are fast at the end, and you combine them and you get something even more powerful. The other thing is that weird trick where you take an n log n algorithm and you turn it into an order n algorithm. And the keys here, if you want to go and do this in your own work, the key is, first of all, you need to be able to divide it into subproblems of size log n that are easier to solve together. So in this case, we have trees of that size, so we can talk about, like the depth first search is this bit vector, and then we know that there are only so many possible subtrees. Or you can talk about Catalan numbers as like the number of trees of the right shape. And usually you want to just reduce the number of possibilities so you can share the pre-processing cost. And then you just solve the n over log n subproblem, and you have to be able to combine the results. But once you do that, you're done, and you have a linear time algorithm all of a sudden. And this technique is also used in the LCA problem, which is why I did both of these papers, because it's nice to see it twice before you kind of really understand what's going on. And that link is the video if you want to see it again. And that's it. So thanks. Any questions? Yeah. Teaching. No, I don't know what this one is used for. The LCA problem is actually used for a lot of things, but this one is just, it's a cool thing to do to a tree. So. Oh, well, I don't know. It's a weird trick. It's a joke. Come on. What's that? Yeah. Mm-hmm. Yeah, so you have to be able to, first of all, like, break your problem into something of size n over log n. Trees are usually easy to do this for. Break it into one subproblem that's smaller of that size, and then be able to solve the rest of them quickly, and be able to merge the results of a query in the micro problem and the query in the the fancy algorithm. You have to be able to merge those results in constant time, but then you can just do this. So like in the LCA problem, what you end up with is you have this array that stores the results of doing the query in sort of a piece of size log n. So you do, I'm explaining this badly. You have an array. You break the array up into chunks of size log n, and then you do essentially one query for the whole thing. You store those results as integers in a higher array, and then you do the fancy algorithm there. And so if you have any arbitrary query, if your query is exactly the size of one of these chunks, then you just have the answer there. But if it spans these chunks, you sort of have to be able to say, all right, well, I'm going to do the query in the small tree in the small chunk here. I'm going to do the query in the small chunk here. I'm going to do the query in the larger piece, and then I'll unify those results. And it's just 3 operations and 2 comparisons, and you're done. So that's OK. So you have to be able to do all of these things, but then you can kind of take any of these algorithms that is n log n, and there's a lot of them, and try to apply this trick and get a little bit better bounds. Yeah, least common ancestor. And it's also related to range minimum query. Going through the paper, you actually, I don't want to give anything away. You reduce the problems to each other, essentially. Yeah. Because you want to do this cute math here. So if you have log n over 4 nodes, you're going to, the number of bits is 2 times the number of edges. So you want this half to still be here so that you can get a square root. That's the reason for that. Yes, exactly. Yeah. Sorry, this is for general trees. We're not talking about trees in a data structure sense. We're talking about them in a graph sense. So a tree is just a graph with no cycles, and you pick some node as the root. So it could be super bushy. It could be like a Facebook graph. I think all of their graphs probably have cycles, but it's a general thing. It's not about a tree that you would be inserting and deleting from like a database or something. Anyone else? Okay, so they were both written by the same 2 people, my professor, Michael Bender, and his colleague, Bender and Farach-Colton. And in both papers, they basically took an old problem that was sort of interesting and had a nice history and had some optimal result. People knew how to do this in optimal time, but they essentially took the paper, took the result, and wrote a paper about doing it in a simpler way. And in this particular case, the previous result, the constant in front of the linear time preprocessing was astronomically huge, and it was a huge problem, right? We have the same thing with Chazelle's triangulation algorithm for people that know geometry. Yeah, it's linear time, but holy crap, does it take a long time? So in this case, they basically simplify the results. And in both papers, they do actually go through a series of steps of more and more complicated algorithms. And in both cases, you use the n over log n trick to get the best results at the end. And that's why I did both of them, is because they're related in this nice way. And they're actually written, I think, around the same time. And the LCA won it won the Test of Time Award for the Latin, the conference, just because it was making this algorithm finally accessible, basically. Yo. Yeah, so, sorry, I guess I've been talking like this, and now I'm talking like this. So why fast trees also do this. It's a data structure invented by Willard. I can give you a reference later if you want. I forget what else, but I think exponential trees might use them too, but it'll take a little bit to jog my memory. But these are the really easy examples to see. For this problem in particular? This is the simplest and most optimal solution to this problem that I know of. I have not dug in to try and find other solutions, though. Yeah. Should we take the rest of the discussions to a bar? Cool. It's over there? All right, cool. Thanks, everybody. Hope you liked it.